In this section, we need to talk how we can perform operations on functions. Most of these are very easy for you based on your knowledge of just how to work with variables. Let's define three functions. Let's define f of x to be equal to x plus 1, g of x to be equal to x squared minus 1, and h of x is equal to the square root of 4 minus x. So now let's actually create one more too. Let's make I of x equal to x squared minus 3x plus 2. So functions have operations just like you have operations with numbers. We can obviously add them. So for example, let's take g of x and add it to I of x. Therefore that would be equal to x squared minus 1 plus x squared minus 3x plus 2. If we combine like terms, we have 2x squared minus 3x plus 1. That's it. We can obviously subtract. So for example, we could take I of x and subtract out g of x. So we have x squared minus 3x plus 2 minus g of x. When you do g of x, be careful. This is the mistake people often make. They don't distribute the minus sign. You'll see me throughout the year and into next year always distributing this minus sign by putting parentheses here first to remind myself to do it. So when we do this, we get x squared minus 3x plus 2 minus x squared plus 1. Notice those cancel, and we're left with negative 3x plus 3. So we've added, we subtracted. The next major operation obviously would be multiplication. Let's take f of x and times by g of x. So that would equal x plus 1 times x squared minus 1. So in this problem, this would be a foiling problem. We distribute x, we get x cubed minus x. We distribute 1, we get x squared minus 1. So our answer is x cubed plus x squared minus x minus 1. We can obviously divide. So if we take f and divide it by g, we get x plus 1 over x squared minus 1. We can simplify this to x plus 1 over x plus 1 times x minus 1, which equals 1 over x minus 1. I have to make this very clear. This does not equal this. In this one here, this says that x cannot equal negative 1 and 1, because that would put a 0 in the denominator. Over here, we're saying x cannot equal 1. It's important to understand that this would actually find a value at negative 1, even though negative 1 does not exist over here. And that's due to the previous lesson where this is a whole, and this also relates to calculus. Therefore, we must put a restriction here, that x cannot equal negative 1. Now it's equal. This restriction makes this statement true. So we've done addition, subtraction, multiplication, division. Now comes the good stuff. If we take number 5, and we call it a composite. So for example, we'll take half. What this really means is you take f of x and plug it into h of x. That's another way of writing it. So for example, h of x is equal to the square root of 4 minus the x value. That x value is f of x. So let's plug x of x in there. Therefore, we get the square root of 4 minus x minus 1, which is the square root of 3 minus x. That leads me to the domains. We need to be able to realize what the domains are in these functions. If we go back to number 1, number 1 has a domain of all real numbers. Why? Because the domain of G is all reals. The domain of F is all reals. The domain of I is all reals. So if we add these together, we're going to still have all real numbers. If we subtract these, we're still going to have all real numbers. If we multiply, we're still going to have all real numbers. When we divide, we have all real numbers up on top, all real numbers on the bottom. But we got to make sure we include that. So my point being is this. The domain of the first 4 operations, addition, subtraction, multiplication, division, are always the domains of both of them combined. Or basically of the one with the least domain restriction. So, in other words, we always pick the domain that covers both of them. So for example, if one of these did have a domain restriction of x is greater than 4, then this would be x is greater than 4. But since both are all reals, it's all reals. The only thing you have to remember is with division, we must include the denominator. So it's a domain that is in both of them, minus whatever restrictions it now has because you divided it from the bottom. With composites, it's very different. With a composite, first and foremost, this is your initial domain. That's what sets everything up. That domain must hold. Once you find that, you then look at the final domain and decide, is that still valid? So for example, here the domain of f of x is all reals. So then when we come down here, we know that we have at least a domain of all reals. But then when we look at the square root, 3 minus x, we realize that x must be less than 3, less than or equal to 3, because if you had 4 here, it would be a negative number inside the square root. So now, therefore, the domain is x is less than or equal to 3. Let's do 1 or 2 more with the GOF, with these composite functions, because they're the domains that usually trick you up. Let's take one, number 6. Let's take GOF. So again, we take f and we plug it into G. So G is x squared minus 1. If we plug f into that, we get x plus 1 squared minus 1. The domain of f is all reals. You can see with this product here, we have x squared plus 2x plus 1 minus 1. Or in other words, x squared plus 2x. This domain is still all reals. So this domain stayed all reals. But now check out this one. This is the one that you'll love. If you take the square root, or let's take GOF. So in this one, we take G, and we plug in H. If you square this, you get 4 minus x minus 1, which is 3 minus x. You would think the domain is all reals, but if you actually, and I would advise you to put this in your calculator, you'll see that the domain is not all reals. In the end, the initial domain up here was x had to be less than or equal to 4. So when we come down here, that must be the minimal domain. This has to stick. There's no way we can ever plug in these values, anything other than these values. So when we come down here, we have to check to see if there's any further restrictions on that. Since there is not, this is your final domain. if for some strange reason this would also exclude x equals 1, then we would add that to that domain. And one final problem, just to kind of make a point. Let's add g of x plus h of x, just to clarify the domain. If we do this, there's really not much to do. We get this. So you can see that the domain is simply the domain of h, because that is the lesser of them. This one has a domain of all reals, this one has a domain of x must be less than or equal to 4, therefore that is the domain of the whole thing. Simple as that. So with that, we'll continue with this a little bit tomorrow, analyzing a few more things with the operations of functions. Have a good night.